like to just wrap up from where we left off yesterday. Yesterday we were talking about solubility curves, first with solids in liquids and then with gases in liquids. And for a gas, here you've got a solubility curve of a bunch of different gases. The one thing to really notice is that these solubility curves go down. So that means as the temperature rises, actually less of the gas is dissolving. So here's one question we were just doing at the end of class, which is if it's 10 degrees, so here's 10 degrees Celsius, what's the solubility of oxygen gas? So we go up at 10 degrees to oxygen gas, that's this green line right here. You can see that because of our legend here, oxygen gas is green. And then you go over to the y-axis, tells you solubility in units of milligrams per 100 grams of water. So often we talk about grams per 100 grams of water, but we're going to use milligrams here because so little of a gas dissolves in water, right? Gases are not super soluble. And then we just look which number looks about right here. Well, if this is 4, that's 6. It's a little more than 5. So 5.3 milligrams per 100 grams of water seems reasonable. Let's put an application here. So let's think about what's going to happen to dissolved oxygen in the water near any kind of manufacturing plant that uses water to cool its equipment from Lake Ontario. And there's lots of manufacturing plants that do this, right? It's very convenient if you build your factory right on Lake Ontario. You can just pour the water over your equipment. And that seems pretty neutral. All you're doing is heating up the water a little bit. But what does that do to dissolved oxygen? Well, let's think about it. So as the water heats up, oxygen gas is going to become less soluble, right? As our temperature increases, you can see this solubility curve goes down. So less oxygen is going to dissolve in the water in that local area where the water is heated. So it's not like the manufacturing plant is going to heat all of Lake Ontario, but in its local area near the plant, you're going to get warmer water. That means that less oxygen dissolves in that water, and that makes it more difficult for fish or other organisms that need that oxygen to survive. So just something to be aware of with dissolving gases in liquids, that increased temperature actually decreases the amount of dissolved gas in that liquid. Two other things are that where temperature doesn't impact so much are liquid solutes and liquid solvents. So that's if you're just mixing one liquid with another liquid and you're trying to dissolve two liquids together, temperature doesn't have a really big impact on that. So you can dissolve about the same amount of liquid in liquid regardless of the temperature. Same idea for gases in gases. So dissolving one gas in another, it's not going to make a big difference if you increase the temperature or decrease the temperature there. Last thing we're going to look at here is pressure and solubility, and specifically we're going to talk about pressure with gases. We'll learn in our very last unit that pressure has a really big impact on gases, and so it also has an impact on gases and their solubility. Basically, the more pressure you put on a particular gas, and this is the pressure of that particular gas. So you can pressurize a gas by just sort of adding more molecules of that gas, by decreasing the volume that it's in. We'll talk about more of that in our later units. But if you increase the pressure on a particular gas right above a liquid, more of that gas is going to dissolve into the liquid. So increased pressure on a gas means more dissolving. And a classic example is, of course, a pop can. That's why your pop can is sealed off. There's an increased CO2 pressure inside the pop can. And as soon as you crack open that pop can, you can kind of hear a hiss, right? That's that pressure getting released. And as soon as you open it, CO2 starts to come out of the solution. So it undissolves. It comes out of solution in the form of bubbles. And of course, because we talked about temperature, increased temperature decreases dissolving. If you warm up that pop, it'll undissolve even faster. Even more of that CO2 will come out of solution. So pressure helps keep that CO2 dissolved in its solution. Another situation where you have to worry about this is scuba diving. So scuba divers breathe compressed air underwater. So this is air under pressure. And air is mainly nitrogen, right? 70-ish% nitrogen is in air. But because it's pressurized, and as you go down into, the deeper you go, the greater the pressure you feel, then that means that you'll have a higher rate of solubility of nitrogen gas. So the nitrogen gas will actually get dissolved into your bloodstream as you dive deeper and deeper into the water. This is something the diver has to be really careful of when they come up to the surface. They have to return to the surface relatively slowly so that that pressure decreases at a slow enough rate that it can slowly undissolve from their bloodstream, so that nitrogen gas can become undissolved in the bloodstream rather than just quickly coming up. If they come up really fast to the surface, then that nitrogen gas will actually form bubbles of nitrogen, of air essentially, in their blood. That could be very painful and also potentially lethal, so pretty dangerous. Last point is just on the rates of dissolving. So this is thinking about how you dissolve one solid into a liquid solvent. So this is what we're doing a lot of the time with dissolving. Maybe you're dissolving sugar in water or salt in water, any sort of solid solute into a liquid solvent. There's really three things you have to worry about to impact the rate of dissolving. The first is stirring or agitation. This you totally know if you've ever made coffee, right? You put some sugar in. If you just set the sugar in, it'll take a while to dissolve in the coffee. If you give it a quick stir, it'll dissolve right away. So a little bit of stirring, it can impact your rate of dissolving. The next thing is, of course, temperature. If you put sugar in cold water, it'll have a lower solubility, less will dissolve, and it'll also take longer. If you heat up that water, it'll dissolve a lot faster. And the last thing is surface area. So if you grind your solid solute, you'll increase its surface area and it'll dissolve faster. So this is essentially what you're doing when you're making the coffee grounds. If you just stuck coffee beans in a cup of hot water, you would get a little bit of coffee, but it wouldn't be very strong. It would probably taste pretty bad. But if you grind up those coffee beans first and increase their surface area, a whole lot more will dissolve and it'll dissolve a whole lot faster.